In question 2, we were asked to look at the impact of temperature on microbial growth. The question asks us to draw a graph to represent the growth rates of heterotrophic bacteria at the average summer temperature and at the average winter temperature. So the average summer temperature is 20 degrees and the average winter temperature is 7 degrees. The Monod equation will be used for bacterial growth, as defined here. So mu represents the growth rate measured per day, and mu max is the maximum growth rate also measured per day. S is the substrate concentration in grams of BOD per meters cubed, and Ks is the Monod coefficient, or substrate affinity, which is the substrate concentration when the growth rate is half of the maximum mu. We were also told that the growth rate is dependent on temperature. Mu max at temperature T can be found by using the following equation, where mu max 20 is the maximum growth rate at 20 degrees Celsius. Theta is the value to correlate the temperature dependency of mu max, and T is the temperature in degrees Celsius. We were told a number of things. Firstly, that the Monod coefficient is 5 grams of BOD per meter cubed. Furthermore, at 20 degrees, the maximum growth rate is 6 per day, and the theta value for temperature dependency of mu max is 1.07. So let's calculate a generic formula for the growth rate at the summer temperature of 20 degrees Celsius. So we know that the growth rate is equal to the maximum growth rate times the substrate concentration divided by the Monod coefficient plus the substrate concentration. So in the case of 20 degrees, we already know that the mu max is 6. And we know that our Ks, or Monod coefficient, is 5. And the units are going to be per day. Now for winter, we need to correct for temperature. So we can use our temperature dependency equation. So mu max at 7 degrees is going to be equal to mu max at 20 degrees times theta to the power of 7 minus 20 degrees Celsius. Which is equal to 6 times 1.07 for our theta value to the power of 7 minus 20, which gives us our mu max at 7 degrees of 2.5 per day. So we can write our formula. The growth rate is equal to mu max times the substrate concentration divided by the Monod coefficient plus the substrate concentration, which is equal to 2.5 times S divided by 5 plus S per day. This is with S being equal to the substrate concentration, measured in grams of BOD per meters cubed. So our generic equations for the growth rate in summer temperature is 6 times the substrate divided by 5 plus the substrate. And for winter time we have 2.5 times the substrate divided by 5 plus the substrate. So in order to draw a graph, we need to vary the substrate concentration to show the growth rates. So we're going to calculate for when the substrate concentration is 2.5 grams of BOD per meters cubed. So the summer growth rate will be 6 times 2.5 divided by 5 plus 2.5, which equals 2. The numerator and the denominator are both in grams of BOD per cubic meter, so that cancels that. Therefore the units are in per day. Well, and then we fill in the table 2. And similar for the winter, we have 2.5 for our maximum growth rate, 2.5 for our substrate concentration, divided by 5 plus 2.5 is equal to 0.83 per day. We also fill that in our table. Now we also calculate this for a number of substrate concentration. I start with the growth rate for the summer. So that's going to be 3, 4, 4.8, 5.1, 5.3, 5.5, and 5.6. For the growth rate of the winter, the values are as follows: 1.25, 1.67, 2, 2.1, 2.2, 2.3, and 2.35. So based on this data, we can now draw a graph. So let's start with the summer growth rates. So at 2.5 we have a growth rate of 2 per day. At 5 we have a growth rate of 3 per day. At 10 grams of BOD per cubic meter we have a growth rate of 4. At 20 we have a growth rate of 4.8. At 30 grams of BOD per cubic meter we have a growth rate of 5.1. At 40, 5.3. At 60, 5.5. And at 80, 5.6. So in summer we can see that depending on the substrate concentration we get the following growth rate curve. Now we will draw the growth rate curve for the winter. So we can see that at 2.5 we had 0.83, at 5 we had 1.25, at 10 grams of BOD per cubic meter we had 1.67, at 20 we had 2, at 30, 2.1, at 40, 2.2, at 60 we had 2.3, and at 80 we had 2.35. So if we match the dots and draw the curve, we can see that at lower temperatures we have much lower growth rates. We can think about how this will impact our BOD removal.